I want to introduce a new force called the normal force. This is the third of the 4 forces that you will be asked about on the exam. So this is the support force from a solid surface. This is what keeps solid surfaces solid. You can't just go in there, okay? They say, hey, I'm solid. What are you doing? You can't come in here, okay? And as with all forces, we want to come up with understandable rules about size and direction that we can apply to every problem. I guess I should first tell you my notation. Normal force I will notate as n with a vector hat. And if I just want to refer to the size, I'll call it n. As you will probably remember, that is also already been in use for something else, so we will get such weird statements as n equals 10n, and not even blink an eye, even though that seems like mathematical gibberish, because we are using n as a variable to indicate newtons, right? All forces are measured in newtons. That's a unit. And this particular force happens to be a normal force. This is the size of the normal force, and that is a variable. So 2 different usages of the letter n in the same context. Lest you think this gets hugely confusing, we are simultaneously moving to a symbolic approach, so we don't really ever see a number followed by a unit unless it's at the very end of a problem. Okay? I should mention, by the way, this is not the first time we've used a same letter twice for 2 different things. I'll give you another example. What's m mean as a unit, lowercase m? Meters. But as a variable, lowercase m means what? Mass. And as a prefix, lowercase m means milli. So we've already used the lowercase letter m 3 times. Okay, this happens. There's only so many letters. You're going to have to get used to it. Now, some books will write normal force like this. But I'm here to tell you that even if we avoid it in this case, we are going to start doubling up on plenty of stuff. Might as well start now. Okay. So let's talk about the rules of thumb for normal force. The direction is probably the easiest thing to start with. If I have something that's on a surface, gravity pulls down on it. If it doesn't move down, then of course the surface has to hold it up. Those exactly cancel. That's the whole idea of the normal force. It protects the structural integrity of the surface by not allowing the object to fall into it. Now, a common misconception then is that the normal force is always up. It's not always up. It happens to be up because here up is needed to protect the surface. Now, if this board is a vertical surface, right? So I can't push horizontally into it because that would be putting my hand through the wall. So in which case how does the surface act now to prevent this? It goes this way, right? And if I had a diagonal surface, like this one, let's see if I can tilt this a little bit, like that, okay? The surface doesn't mind if I go along it. There's friction, but that's something else. Friction, of course, doesn't stop me. But if I try to go directly into it, no way. So it pushes directly away. So it can even be diagonal, right? It's just perpendicularly away from the surface. It just most directly says you can't come in here. In fact, that's where the normal force gets its name. Normal is an old word for perpendicular. It's a force which prevents you from going somewhere by directly pushing out to prevent that. Okay? Now, as far as the size goes, it depends on the situation. The only thing that the normal force seeks to accomplish is to block you from coming in there. Okay? So the size will vary, and the amount that it will push is exactly to prevent, I guess I'll write it here, smushage, okay? So the surface doesn't want to get smushed. That's the only thing it's looking to do. It's protecting the structural integrity. If 3 newtons are trying to get in there, so there's some force pushing in there that's 3 newtons, it pushes 3 newtons back, right? If you try to push in 5 newtons, it pushes 5 newtons back. That's the only thing that it's trying to do. And for us, our surfaces are not going to break, so if you need the surface to push back 1,000 newtons, then we're okay with that, okay? So let me give you an example. In this case, of course, the normal force is going to have to be exactly equal to the force of gravity because that's what's endangering the surface, right? Now, I'm sorry to report that this ends up becoming a knee-jerk habit. The students will plug in because it's the first thing I said, and they're like, okay, I got it, don't need anything else, okay? So let me show you right away a situation where that is not true. Let's say I have an object on a table, but in addition to a force of gravity threatening the surface, I'm going to push down on it too. So I have a pushing force that I'm making the problem worse. Okay? Well, now the surface has to do double duty, right? It has to kill both of them if it's going to protect the surface. In this case, the normal force has to kill both of them, right? Not just one, but both. Whatever forces are threatening the surface, it's got to kill them. If I had 17 forces going into the surface, it'd need to kill all 17, right? Now notice in this case, of course, the normal force is greater than the force of gravity because gravity is not the only thing that it needs to fight. There's a homework problem you have where you can go the other way, which is to say, maybe you lift it instead of pushing down on the object and making the problem worse and giving the surface more to do, maybe you give the surface a little relief. So you kind of, instead of you have an object like this where you push down, you're going to like partially lift it. Like you're not going to actually pull it hard enough to actually lift it off the surface, but you're going to relieve the gravity a little bit, right? So in that case, let's do an example. Let's say I lift it. Let's say gravity is 10 newtons, but I lift off with 1 newton. So how much force is pushing into the surface now? 9 newtons. So what does the normal force need to cancel? 9 newtons, right? It just does whatever job is necessary to keep that object from going in there. So make sure you understand that the normal force is always going to balance things out. It's never going to be harder. It's never going to push harder than it needs to. It's never going to push lower than it needs to. It's just whatever is needed to protect the structural integrity of the surface, or more informally, prevent it being smushed. Okay? So that's the simple rule of thumb that we're going to introduce whenever we have an object on a surface. Let's go ahead and do an example problem using that. Have any questions before I clear a little space? Okay, so this is going to be our first encounter, but by no means our last. This is going to persist throughout the course with what's called an inclined plane. An inclined plane simply meaning a tilted surface. So we don't want all of our surfaces, we don't want to always be having our action happen on a horizontal surface. So let me go ahead and put a tilted surface here, and I'm going to give you some givens. I'll give you the angle theta that this surface is tilted above the horizontal. I'm going to put a mass on it, which I'll call mass m. And the number delivery truck is running late, so we're going to have to formulate our response as a symbolic solution. So think of it like there's a number delivery truck. They say, yeah, we'll get you the values for m and theta later, but why don't you do what you can in the meanwhile, okay? I'm also going to have to tell you that this surface is frictionless, so you're going to have to imagine a hypothetically perfectly smooth surface, which of course doesn't really exist. Imagine maybe a Teflon frying pan or some ice or something that's very smooth, but then that much smoother with no friction. Such a thing doesn't actually exist, of course. And here's what I'm going to ask. I'm going to ask, what is the size of the acceleration that this mass will experience? As you can probably imagine, it will slide down. It can't stay there if there's no friction to hold it there. And I want to know how much acceleration that is. And I also want to know how much force does the surface have to exert on that object. So here's our first chance to take the problem-solving strategy out for a formal spin. Okay? 1, object of interest. Got to be that mass. Pretty obvious. You might wonder why this step is even there. It's because sometimes it's going to get a little weird. It's not going to be clear. But for right now, step 1, piece of cake. Step 2, identify forces that act on that. Can anyone tell me a force that acts on that mass? Normal force, for sure. Which direction does it act? Perpendicularly away, like that. Okay? What's another one? Gravity, right? Which way does that act? Straight down, okay? So be careful. A lot of students have it pointing this way. That's not right, okay? If that's the case, I want to see you walking up a hill in San Francisco and jump up and down like this, okay? You can't, right? It's still vertical, okay? Gravity's still acting vertically even if the surface is tilted, okay? Do we need to include a tension? No, there's no rope involved, right? We only include a force if it's relevant, right? Tension's included if there's a rope attached to our object of interest. Normal force is only included if the a solid surface is touching the mass, right? All right, steps 1 and 2, done. So, step 3, here's our opportunity to try step 3. Is the acceleration going to be 0? No. Okay, which way is it going to accelerate? Do we know that? It's going to slide down. So what we're going to do is we're going to choose our first fairly strange axes. If you're wondering why on that vector practice sheet I had all these weird bent axes, it's because we need those kind of things. Now, you might question, why would we do that? Well, it's great because now our question of what is the acceleration comes down to simply finding what it is in the x direction, because I set the x direction where I know it is the only acceleration. It has no y acceleration at all. I've defined the y-axis in a way that I know that it doesn't move that way. Right? It doesn't move in the plus y direction. That would mean it would just jump up and fly away off the incline, right? But it can't move in the minus y direction either because there's a surface there that is not going to allow it to do that. It's a lot easier to find the acceleration when it only has a single component. That's why we do this, right? That's why we choose, if we know the direction of the acceleration, we choose one axis along that. So that's our chance to see that one. Now we got to just break our force into components. Well, this is the first time with some bizarre components that the force of gravity, we can't say that's negative. It's not negative x. It's not negative y. In fact, the force of gravity is now diagonal relative to those axes. If you want, you can take your paper and go like this. Whoosh, okay? And what would that look like? It would look like this. So this is the tilted view, right? Tilted view. The normal force acts perpendicularly away from the surface, but the force of gravity actually looks like this. Right? If you don't believe me, tilt your paper and it'll look just like that. Tilt it until the line that is on the incline is going horizontal to you. So we got to break the force of gravity up for the first time. Now I know the size of it is mg, right? And you can see here why we would not want to include the negative in the g, because it would be a total booby trap here. That's not, the hypotenuse is not negative, it's not anything, right? I'd have to break this up into components, like this. So that's diagonal. It has a minus y and a plus x component. So this is a minus y component, and this is a plus x component. We can, of course, use plus and minus for the components once we've defined our axes, but the hypotenuse is nothing, right? There's no minus in the hypotenuse, okay? So our goal is to do that, and the first thing I should prove to you, and I should put the components over here. So this is my minus y component. This is my plus x component. Be really careful in how you draw that. Again, make sure that the entire force is the hypotenuse, right? The entire force is the hypotenuse. It's the biggest side, and you're trying to break it into two smaller pieces. I see lots of different ways this triangle goes wrong, okay? So make sure that the entire force is the hypotenuse. These two components could also be described as perpendicular to the surface and parallel to the surface, right? That would be another way to describe them. There's a part of the force that acts into the surface, and there's a part of the force which acts along the surface. So the first things first, I need an angle to use, and so I'm going to do a quick proof, and this is something that I'm going to show you once. Remember the result, never try to do it again because it's a big waste of time. So if you, let me redraw this over here, maybe it'll make it a little easier to make the object a dot. And I'm going to extend my force vector a little bit longer. There are probably a bunch of different ways to do this geometry, but I try to keep a minimum of geometry in my head. One thing I can remember is that the interior angles of some of the interior angles of a triangle is what? 180. Yeah. So I'm going to look at this triangle right here. This angle is already 90, so if this is theta, what is that? 90 minus theta, right? If the interior angles have to add up to 180, and one of the angles is already hogging 90, the other two have to add up to 90. Okay? And then I can also realize that this is perpendicular. By definition, that was a component into the surface, right? So these two have to add up to 90 as well. Okay? So if this is 90 minus theta right here, what does this angle have to be? It's back to theta. Okay, we're done. Did it once, never have to do it again. That's nice. The very angle that I needed to do my SOHCAHTOA on the force of gravity is actually the same as the tilt of the incline. Done. Don't ever have to do that again, because we'll be doing so many inclined plane problems, you're just reinventing the wheel. Just remember that when you're breaking up the force of gravity like this, the angle is the same as the angle of the incline. So which side is this? Is this the adjacent or the opposite? Adjacent. So does that get cosine or sine? Cosine. All right, cool. Minus it's a minus y component. Hypotenuse times cosine. This is the positive x component. It's the opposite side, so that is sine. It is worth mentioning, just because so many people I have seen always want to put the cosine with the x component. In this case, the cosine goes with the y, because we have this weird flipped around triangle. So remember, cosine sticks with the adjacent side. Sine sticks with the opposite side. That you can always count on. The orientation of the triangle will determine if the opposite side and adjacent sides goes to the x or y or the other way around. All right, cool. So we got that done. Do we need to break the normal force into components? No, we don't. That we got lucky. That is simply along the plus y direction. So, done with step 4, and let's move to step 5. Always like to do a good free body diagram. It's always worthwhile. Here's what we have. So here are our pushes and pulls broken down into individual competitions on the x and y axis. And what we have is that the force of gravity in this case is convenient to think of in two different parts. We are basically thinking of the force competition along the direction that's perpendicular to the incline. And the reason why perpendicular is important is this. The normal says, nope, nice try, buddy. You can't come in here. So the force component, which is going to be offensive to the surface puts a stop to that. But there is another component of the force of gravity which is parallel to the surface, and that is going to be what initiates the acceleration. In fact, it causes the acceleration on the way down. So we have that the surface cancels some of the force of gravity, but not all of it, and the remaining is what causes the acceleration. This problem is really no different than if I gave you a problem where there was a plus 2 Newton force, a minus 2 Newton force, and a plus 3 Newton force. You look at that and go, yeah, all right, I get it. This kills this, and this just makes it go. So what we have now is just tilted. It's tilted to the side, right? So let's go ahead and finish up step 5 and 6. So step, the x direction, we have one uncontested force, and it is going to cause an acceleration. In fact, we can solve here. The acceleration in the x direction is plus g sine theta. Now, you could say, isn't that just the x component? Well, remember, we designed it so the entire acceleration was that way. So that's actually the whole thing, too. In the y direction, we have a competition. If there's any remaining left over, you would have y acceleration, but we purposely made it so there was no y acceleration, which of course means pretty much what the free body diagram told us, that the normal force cancels off a part of the force of gravity. Not the whole thing, by the way, okay? The normal force in this case doesn't need to kill the entire force of gravity. It just needs to kill a part of it, the offensive part of it, right? Okay, so here are my answers. The normal force is this. The acceleration, I guess just to be proper, this is the x component. The y component is nothing, so you don't really need Pythagorean theorem to find the magnitude of the entire acceleration, although it would be work. The acceleration as a whole is, of course, g sine theta. So those are our answers. That's solving the nuts and bolts of the problem. It's going through steps 1 through 6. I want to discuss these results a little bit more on Friday, but that is the end of the calculation. Okay, so that's it for today.